Mic off. Mic off. Mic off.
Oh. Ooh. Um, hope you all are doing all right here. Um, yeah, so I posted I think 4 problems on on Nopal here. Um, so I do have myself muted in um, Google Meet. So actually, I'm gonna unmute myself there real quick. So if you have both audios up, you're gonna hear me double. Just a warning. All right. So my idea here is to sort of like I'll do the work and do the talking on the YouTube stream here, but sorry, wanted to get rid of this. Um, so I'll have myself muted in Google Meet, but if you have a question at any point, just sort of chime in here on Google Meet. I'll have that audio up, and then we'll answer some questions that way. So I'm gonna mute myself again over here on Google Meet. All right. Let me go ahead and pull up this list of questions real quick. So I'm gonna temporarily get rid of that while I log in here. Yeah, sorry, I thought I actually posted these questions earlier in the day when I made them. Apparently, I logged into the site and then went to the page where I was going to put them and didn't do it. So that was a good job. Yeah, so there's a folder under documents called problem set. And that's where these files will be. All right, here we go. So these are the questions we'll do. We'll work through these 4 questions, and hopefully that helps with maybe understanding the videos a bit more. Hopefully those were pretty good, or at least usable. Actually, I have a camera. Let's go ahead and pop that on. Why not? Yeah. I hope you guys are doing all right, though. All right. So we'll just get right into it here with this first question. So we have a box with a square base and an open top must have a volume of 32,000 cubic centimeters. We want to find the dimensions of the box that minimize the amount of material used. So let me go back over here to this blank document I made. So for question 1, right, so with these optimization problems, the goal is always to say, like, all right, well, what is the thing I'm trying to maximize or minimize, or the thing I want to optimize, and then list out any constraints, right? So in this case, we'll start by drawing a picture to see what's going on. So in this case, we have a box with a square base and no top. So I'm try my best to draw a box with a square base. All right, so here we have a box. All right, and I want to emphasize that this side, there is no top here, right? And, if we're going to work with, in this case, the volume of this stuff, we want to give these sides some letter. Let me call the base here. Both sides of this have length x, and again, that's because it's a square base. And then the height of this box will be h. Right? So now we have to figure out 2 things here. We need to figure out the objective function. Right? The thing we're trying to optimize, and any constraints that go with it. Right? So when we look at this one here, we're looking at, let's see. So we're trying to minimize the amount of material used. So in that case, when we're trying to minimize the amount of material, we're asking about basically, how much area of cardboard would we use to build the box, right? So in that case, there's sort of the 5 sides that we want to add up the area for. It's supposed to be pointing at all 5 sides of this. Remember, it's only 5 sides because there's no top here. So this objective function, let's call it, I don't know, A for area, I suppose. And I want to add up all these different areas. So the base, the bottom of this box, is a square, so it has area x squared, right? And then the sides, the 4 sides of the box here, they have base x and height h. So each one of those has area x times h, but there's 4 of them, so we have 4xh. And that's going to end up being our objective function here. Right? All right. So now that I have the objective, what is the constraint? Well, the constraint is that this box must have a volume of 32,000 cubic centimeters. So that constraint then goes to say that, let's see, we want the volume. So the volume of this thing is x squared h, right? Length times width times height. And this has to be 32,000. All right. So that's all the information we need. Now we want to go ahead and cut this objective function down to a function of 1 variable. Right? So the easiest thing to do here is we want to look at this constraint and figure out, well, what variable can I solve for? And turns out that h is the easiest one to solve for here. So we get this, and we just toss this into the objective function, right? So I'll call this one variable objective. So let's see, what are we going to get? We're going to get x squared plus 4x times this stuff. Right. Oh, my drink is empty. All right. Okay, so let's go ahead and multiply this out a little more, since we're going to have to work with the derivative of it. Let's see, 4 times this is 128,000 over x, right? And now we have to figure out, well, what kind of feasible domain is there? Right? What range of x values can we use here? Well, the only thing that really makes sense here is x greater than 0. Right? So often what you do in this kind of situation is, you'll take this area function here and you'll set it equal to 0 because you only want area to be positive. But in this case, we can never actually achieve the area equals 0 because of this x on the bottom here. So we just say, like, all right, well, what values make sense to plug into the function? But when we look at this function here, all right, so we know we can't plug in x equals 0, but once we eliminate that, we know we either look at negative x values or positive x values. And at that point, that's when it becomes important to know, like, well, what does this x stand for? This x stands for this length of a side here, and it doesn't make sense to have a negative length. So our feasible domain is just x greater than 0. Right, so that's going to put us into this realm of having to use that first derivative test that we did before. Sorry, I need a drink. All right. Okay. So now that we have this, we want to, well, take our derivative and see what we can get out of it. So a prime that we did before. What was up? What was that? Oh, maybe an accidental mic usage. All right. Anyway, yeah, so let's go ahead and take the derivative here. So 2x, this is going to be minus 128. That's not an 8, is it? 128,000 over x squared. Right, because again, this is just 128,000 times x to the minus 1. So we're going to take this and we're going to set this equal to 0. Right? Now again, critical numbers, they are where the derivative is either 0 or undefined. But in this case, it's undefined at x equals 0, but that's not in our feasible domain, so we don't have to worry about that one. So we set this equal to 0, and let's see what we get. So this is saying that 2x has to equal 128,000 over x squared, right? So I'm just taking this fraction here and moving it to the other side. So multiply this x squared up here. We're going to have 2x cubed is 128,000, which means that x cubed has to be 64,000. And if I can do arithmetic correctly, this should be 80, I think. Right? Cube root. No, not 80. 40. 4 times 4 is 16. Times 4 is 24. Okay. Yeah, so x is 40. All right. So this is the only critical number we have, right? And as I was saying in the lecture videos, hopefully you had the chance to watch them. When we do these problems here and we're on an interval and we have exactly one critical number, then there's sort of only one possibility. If we find out that it's a local max or a local min, because of how functions have to behave at those, and there's no opportunities to sort of have another turnaround in your function, because that has to happen at critical numbers, this has to be either a local or an absolute max or an absolute min. So now we want to figure out, well, which one is it? So we can use the first derivative test. We can also use the second derivative test on this. So let's find a double prime. This is going to be 2. It's actually going to be plus 256,000 over x cubed. Right? Because when we do the derivative here, we get a -2 times this. Right? So now we want to figure out, well, which one is it?
Where are those online lectures?
So we can use the first derivative test. We can also use the second derivative test. You might want to mute your... Alright. I guess I should say, when you unmute your mic in here, it's a good idea to mute the live stream. Otherwise, that happens. Alright. But was there a question at all? Okay. Just wanted to make sure. I hope that's not me that's actually somehow getting a duplicated mic. That wasn't happening earlier. That'd be really weird. Anyway. So now that we have this second derivative here, we want to check, well, if we plug in 40, what's going to happen? So this is 2 plus 256k over 40 cubed. And somehow getting a duplicated mic. That wasn't happening earlier. That'd be... Emma, the lectures are on WebAssign. So there's the 2 types of assignments up there. One set of them are, they sort of have a date and the word lecture afterward. So it's a bunch of videos going through topics like we would normally do in lecture. And then the other one's the normal homework set. I'm looking at where the text is and my camera's over here. So this is something I'll have to get used to. Yeah. Right. Anyway, so we can see here that this is going to be a number greater than 0. Right? We don't even need to know what number greater than 0 it is. We just need to know that it's greater than 0. So this is going to mean... Sorry, I did mean to actually write here a double prime of 40, not just a double prime equals. Right? So since the second derivative is positive, that means that x equals 40 is well, really it's an absolute max. Or sorry, minimum. Absolute minimum. All right. So, since we know that, then, well, we just have to use that to answer our question, right? So we want to come back up here to what our equation is for h. And we want to say, well, then, well, that h is going to be gigantic, isn't it? Right, so h is 32,000 over x squared. So it's 32,000 over 40 squared. Let's see. So 2 of these zeros are gone. This is 80. Right? So the dimensions we're looking for then so we should say the dimensions should be 40 centimeters by 40 centimeters by 80. I need to learn how to like drag text in this. 40 centimeters by 40 centimeters by 80. Right. So yeah, so it's always good to sort of like actually answer the question that we're being asked here, right? Which was to find the dimensions that minimize the amount of material used in this situation, right? So, you know, again, just a quick recap of all this. It's a good idea to, you know, draw a picture of the situation, try and write down your objective and your constraints, and then you might notice it kind of has a similar feel, at least up to sort of this part here, to related rates, right? When you have multiple variables, you need to start cutting them down. It's the same kind of thing with the objective constraint stuff. Right. Let's go to the next page here. Okay. So let's see. The second question here. So here we have a farmer wants to fence in an area of 1.5 million square feet in a rectangular field, and then divide it in half with the fence parallel to one of the sides of the rectangle. Right? So how can he do that so as to minimize the cost of the fence? Right? So this problem here. So we have, let me call this problem 2. So we know that we have, let me just write this down, area is 1.5 million square feet. Right, just to make a note of that. And what is the shape that's being talked about here? So we want to fence in a rectangular field. So we're looking at something like this. Right? But then we want to divide it in half with another fence parallel to one of these fences. In other words, we may as well draw it vertically here, because we're just making a picture here. So we're essentially looking at building, you know, 2 adjacent rectangles next to each other. So if we do that, then we have to label these sides. A good way to do that, I would say, is to label each section of this with an X. And then we can label each of these with a Y. Now, of course, we could, you know, label the whole top X instead of X and X. But then it'll be maybe not as good. Or it'll be easier to get the answer that we're looking for if we do these separately. And again, the important part is we're cutting it in half, so we know these two are going to be the same. It's not going to be like 2/3 X over here and 1/3 X over here. Okay. So now's when we need to start figuring out some objective and constraint functions. So objective and constraint. So the objective here, what are we trying to do? We're trying to minimize the cost of the fence, right? So, assuming that we're not going to change fence types or anything like that, the way we would minimize cost for the fence is to minimize the amount of fence that's used. And that would be the perimeter, right? So we want to add up all sides, or all pieces of fence here, and minimize that quantity. So I'm going to call that P for perimeter. Right? But I mean, the letter choice isn't so important. So here, when I look at this shape, I have 4 x's and 1, 2, 3 y's. Right? I hate those sneeze fake outs. All right. So that's our objective function. This area up here is how we are going to get our constraint. So that area is the area of the big rectangle here, right? Which is the sum of the area of the 2 small ones. So the constraint is that, well, let's see. The area of this rectangle is 2x times y. Actually, I don't need to write that part. So that area has to equal this 1.5 million. Yeah, maybe we'll just write out the whole number here. Right, so 1.5 million. All right. So now that we have our constraint and our objective function, same deal as always. Right? So we want our 1 variable objective. So we have to pick a variable to solve for here. I don't know, let's solve for y, I suppose. So this will be 750,000 over x, right? When we solve for y there. Right? And so the perimeter will be 4x plus, let's see, I need to multiply this by 3 now. So that's 2, 2, 2, 5. Is that right? No. That's better. Right, so we're going to end up with this. And we want to take the derivative. We get 4. Oh, sorry. I forgot about the feasible domain. So the feasible domain here, it's the same as the last problem, really. It doesn't make sense to have x less than 0 here, or equal to 0. And there's sort of like no restrictions on the largest x can be from this function anyway. Right? Now, on the other hand, I do want to point out, if instead of given an area constraint like this, if we were told that, the farmer has, I don't know, 1,000 feet of fence or something like that, right? Then, the area would become the objective, the perimeter would become the constraint, and in that situation, we would actually get a nice interval, and we wouldn't have to do this first derivative test stuff or second derivative test. But that's not the example we have. All right. So anyway, back to this. So the derivative here is going to be 4 minus yeah, we always want to make sure what we're working with here for the feasible domain. Because it's, I keep trying to scroll on the wrong monitor. So like, if we don't put this restriction in, there's actually going to be another critical value here, our critical number, for a negative value of x. And, we want to make sure that we don't pick up extra critical values critical numbers that don't make any sense for the problem. And, maybe in this particular one, it feels a little less important. But when you get to the problems that actually do give you an interval, sort of a smallest value and a biggest value to work with, if you don't use that feasible domain, you could pick up, again, extra critical values that, are either impossible, like negative lengths or stuff like that, or are way too large for the problem. Like, values of x or y that exceed the total amount of fencing available, maybe. Yeah, so it's actually always important to have that domain, even if it doesn't feel important for that particular problem. Conceptually, it's an important thing to have around. So hopefully that gives a decent answer to your question there. But do let me know if you have any more. All right. So when we differentiate this, we got 2,250,000 over x squared. Right? Because again, this is just x to the minus 1 here. So now this thing we want to set equal to 0. Again, this function has a critical number at 0, but the function's not even defined there, and our feasible domain is greater than 0 anyway. All right, so let's start solving this. So if we move this over, 4 equals 22503 squared. Cool. This happened to me earlier too. Let me just give this a couple seconds to make sure everyone refreshed. Yeah, OBS likes doing this to me. All right. Hopefully we're good. Everyone's reconnected or refreshed. All right. So here we need 202,250,000 over 4. That's a big number. I can't do that in my head. Okay. 562,500. And then we want to square root that number. Oh, cool. So x is 750. Actually, let me move this over here. Right, so again, here would be one of those places where that feasible domain is important, because when we square root this, we're going to get plus or minus 750, right? And that's where the feasible domain is going to say, don't care about the negative ones, right? Anyway, so let's see, what are we trying to do here? We're trying to minimize this thing here. So we want this to be an absolute minimum at 750. All right. So, all right, well, let's look at the second derivative here. This is going to be actually just 4,500,000 over x squared. Right? So when I plug in 750 to this, One more. Yep. Again, I don't care what this actual number is. I just care, is it positive or negative, right? And here this is obviously positive, so we're dealing with an absolute max, or absolute min. Right? So, now that we have that, we just need to say, all right, well, let's find y. So we know x is 750. So we have 750,000 over 750. So that's 1,000. Right? So what we're looking at is a picture like this, where these are the 1,000 sides, and each of these parts are 750, so this whole thing is 1,500, right, for the whole edge here. So the phrasing we could use to answer this would be the dimensions of, let's see, the dimensions of the field would be, we could say, 1,000 feet by 1,500 feet divided along the 1,500 foot side. Right? So we're dividing it here. Or we could say something like, let's see. Each half has dimension 1,000 feet by 750 feet. Right? So either way you want to write the answer would be fine here, just as long as you're kind of saying, you know, how the subfields are divided. Right? Any questions about this one? I know this is a bit of a longer one, a bit more interesting phrasing for the answer there, but any questions about that at all? Cool. All right. So let's go ahead and get on to the next problem here. Whatever, it's fine. Right. So let's see, what is problem 3? Oh, this is the more geometric one. Right, so I want to find the points on the ellipse that are furthest away from this point 1, 0. Right. So let's see here. Right, so we're looking at the ellipse 4x squared plus y squared equals 4. And we want furthest from the point 1, 0. Right? So what's important is to sort of see, like, what is the situation we're looking at here, right? So let's graph this ellipse real quick. So I'm going to divide by 4 to put this into standard form, right? Standard form of an ellipse has a 1 over here on the constant side. So this ellipse is taller than it is wide. Okay, so it looks something like this. Hopefully that looks about right. Right, and then we're looking, okay, here's the point. Oh, I wrote this backwards. This should be 0, 1. Sorry, so that's a typo in the problem sheet there. That shouldn't say 1, 0. That should say 0, 1. I mean, we could do 1, 0 as well. Oh, what the heck? You know what? It's on there. It's on the problem sheet. Let's keep it 1, 0. It's not that big of a deal. Right, so 1, 0 is this point here. So you want the furthest points from actually this point on the ellipse, which, you know, are probably something like this. Right? Since we have a symmetric object here, it should make sense that there's actually like more than one. Right? So anyway, we need to come up with a constraint and an objective function here. So let's get the objective first. Right. So our objective function here is actually pretty straightforward. And if you watched the lecture video on WebAssign already, you hopefully remember what it is. In this case, we're just looking for the distance from this point, right? From this point 1, 0. So the objective function is the distance from xy to 1, 0. Right? So this point here, you know, whatever these points are, oops. Whatever these points are, you know, they're all at this point, we're just referring to as some generic point x comma y. Right? Now, you might also remember, I gave a whole argument for why it should be true in the lecture video, but this function's pretty complicated to deal with. So since this function is always positive, I'm going to replace f, or I'm going to replace d with something I'm going to call f, and it's just going to be the square of this. And this is okay to do because this function always outputs positive numbers. So I'm never going to, you know, take the minimum being a negative value, square it, and turn it into a positive value. That won't happen. So anything that's a minimum stays a minimum. Anything that's a maximum stays a maximum. Right? So that's our objective function. This is actually our objective function. This is sort of an easier one to work with. So we're going to use f as our objective. The constraint, right? The constraint is like, well, you know, right now we're just saying our objective function is the distance from any point to 1, 0. We want to make sure that we stay on the ellipse, so we're going to stick ourselves with the actual equation for the ellipse. Right? That's our constraint. Right? So this makes sure that the only points x, y I'm allowed to choose actually come from that ellipse. Right? Hopefully that makes sense here. And now the nice thing about problems like this is, you know, I still need to cut this down to a function of one variable. But here I have a y squared, here I have a y squared. So I don't actually have to solve for y, I can just solve for y squared and drop that into the objective function. So if I solve for y squared here, I'm going to get 4 minus 4x squared. And so my one variable objective is going to be x minus 1 squared plus, pop this in, 4 minus 4x squared. All right. And now we do our derivative. Sorry, we need the feasible domain. I keep forgetting this. So what is the feasible domain? Right, what is a feasible domain here? Well, what x values can I plug in? Right? What makes sense to plug in? Well, if we look at the ellipse here, the x values on the ellipse range from -1 all the way to 1. So that's a pretty good feasible domain then. -1 to 1. Or my camera's flipped, so -1 to 1. All right. So let's see what we get. So that's our feasible domain. In other words, x is stuck between these two. All right, so let's look at the derivative. This is going to be 2 times x minus 1. That part's done. This is gone. Minus 8x. So this is -2 minus 8x, or minus 6x, equals 0. Right? And again, this function is never undefined, so we don't have to worry about any of those critical numbers. Let's see, so this is saying that x equals, let's see, 6x is -2, and so x is -1/3. Okay. So now in this case, we are on the closed interval. So since we have a closed interval here, we can do that extreme value theorem stuff. All right, so here we have x, we got the endpoints and our critical number, right? And we want to plug those into f itself. So let's see what happens here. If I plug in x equals 1, or let's start -1, I'm going to have -2 squared plus 4 minus 4. So this is 4. If I plug in 1, I'm going to get 0 squared plus 4 minus 4. So this is 0. And if I plug in -1/3, I'm going to have -4/3 squared plus 4 minus 4/9. Right, so what does that end up being? We get 16/9 plus 36/9 minus 4/9. What was that? 40, 52, 48/9. Right? Which is bigger than 4. So this here, this is the max that we're looking for, right? This is the absolute max. All right. So the question is asking for what are the points? So we know that the x value of the furthest points is x equals -1/3. So now we have to find the y values, right? And as I was saying up here, there's going to be like two of them because of the symmetry of the picture. So when we go back in here, we're just going to say, all right, well, here's the equation of our ellipse. Let's just plug in that minus 1/3. So this is going to, let's say, plug in x equals negative 1/3. That's going to give us 4/9 plus y squared equals 4. So y squared is going to be 32/9. I think I did that arithmetic right. And so y is going to be, let's see, square root of 32. 32 is 16 times 2, so this is going to be 4√2/3, plus or minus, right? So the furthest points are, we have negative 1/3 and negative 4√2/3, and negative 1/3 positive 4√2/3. Right? So it's important to keep in mind, which what exactly the problem is asking us, right? And when we do the calculus and we, solve the parts of the problem here, what parts are actually relevant, all right, or what they're telling us. And again here, when we cut this down to just x, we're only saying like, well, where horizontally on the ellipse are we? And then when we go back to find the y value, we find, oh, there's actually two of them, which again, hopefully makes sense. Right. So technically at this point, class is over. I'm going to go ahead and do the last problem here, just because it's a bit of an interesting one. But, I want to re-emphasize that, I'm not keeping attendance for these problem sessions or anything like that. So if you have other commitments you have to do, by all means, do that. These videos will be, saved on the YouTube channel for you to go back and look at any time. So, figure the more examples you have available to you, the better. So I'll go ahead and do this one. And, yeah, stick around if you can. Otherwise, have a good rest of your day. All right. So let me go ahead and get this last one knocked out here. All right, so problem 4. Let me pull that up real quick. Problem 4 is another geometric one. It's kind of a neat one here. We want to find the point, or find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So that sounds all fancy, but it's not that bad. So let me go ahead and pull this back up. Well, the goal was going to be today, or yesterday, but, plans obviously changed very quickly, so hopefully I can get this done by the end of the week. Since that's my no teaching day. But since I got a lot of the lectures done, hopefully I can get that done sooner. I want to get that finished up. But as far as actually getting them back to you, that's going to be interesting. Because we have a stay-at-home order. So my original plan was to go scan them all and send them to you through email. I'll have to see what exactly I can manage to pull off. I guess the campus isn't entirely shut down, but I don't know if I'm allowed to go in. But I figure if no one's there, it shouldn't be an issue. But the results of them, at the very least, will be up the end of the week here. So, yeah, sorry. All the stuff going on really sort of threw me off. But yeah, no, they should have been back already. Is it true? Didn't quite get. Sorry about that. All right. Here. Right. The area of the largest rectangle that can be inscribed in a semicircle of radius r. So, so if we're going to use a semicircle of radius r, we have to pick a circle of radius r first. So we may as well use the nice one, the one centered at the origin. And since we want a semicircle, we only want half of it. Here, a good idea would be to just say, well, let's make y greater than or equal to 0. Right? Just pick the nicest one. So that puts us in this situation here. Have our semicircle. And what we mean by inscribing a rectangle in here is saying, all right, well, just fit a rectangle inside of here. So which one of these rectangles like this have the largest area? Right? There's all sorts of them that we can draw. Which rectangle is the largest? Okay. Well, one nice thing about these rectangles being inside of a semicircle, however, even though my picture's a little lopsided, so it doesn't look perfect, however far it stretches from the y-axis to the right, it's going to go an equal distance to the left. So, the nice part of this is, if this corner right here is xy, then this corner is minus xy. So I want the rectangle with the largest, I want the largest rectangle. So it has the largest area. Right, so my objective should be the area. Right. So to figure out the area of this rectangle, well, if I go x in this direction and I know I have to go x in the other direction, the area of this is actually just 2xy again, right? So like this half of it is x, this other half is x again, and the height is y. Right? So the objective is this, the constraint. Well, what would make sense for a constraint in this case? Well, if this corner here has to be on that semicircle, then that semicircle equation actually gives me a constraint for the problem. Right? And actually, it comes with the feasible domain already. Which is that y
constraint for the problem.
You got your mic unmuted. There we go. The feasible domain here, right? So y starts at 0, and it actually can only go as high as r. So, 0 to r. well, for y. Right? So it depends on, what variable we're solving for here. So it's actually, I jumped the gun a little bit because I wanted to get this out before I forgot. But it's a good idea to cut your objective function down to one variable first, and then get your feasible domain. So actually, let me bop this for now, because there's a better feasible domain than this. So notice here that y is kind of duplicated. It goes up and back down, but x is only sort of traversed once. So we actually want to solve this constraint for y. In this case, we want the positive square root so that we're on the top half of the circle. Right? And then we're going to plug that into the objective. Right? So this is going to give area to be 2x square root r squared minus x squared. Right? And now we'll say for the feasible domain, the better feasible domain is that x can go from minus r all the way around this to r. Right, so again, let me just emphasize that this feasible domain is for x. Right? Oh, sorry. X doesn't go from minus r to r. X goes from 0 to r. Because remember, this x, we're only considering it starting here and going to r. Because this side, the way we counted it is by duplicating this here. Right, so let me emphasize here that x be positive as well. Right, so again, we're choosing this xy based off this, and then whatever we choose for x here gives us the negative x over here. Okay. And again, that just makes life a bit easier for us. All right, so let's go ahead and take our derivative here. A prime is going to be 2 square root r squared minus x squared plus 2x. Derivative of this thing is going to be negative 2x over square root r squared minus x squared, and then times 1/2 for the chain rule, or the power rule. So this is 2 square root r squared minus x squared. Let's see, let's use this 1/2 to cancel that 2. So minus 2x squared over r squared minus x squared. Right? And we're going to set that equal to 0. Now we're on a closed interval here. So the only critical numbers we need to worry about are the ones that are inside this interval from 0 to r. So you can see here this derivative is undefined when x equals r, but that's okay. We're not going to count that as a critical number because that's our endpoint here. Right? So we're all good. So we'll set this equal to 0. So we get 2 square root r squared minus x squared equals 2x squared over r squared minus x squared. We're going to take this denominator and multiply it to the left side. So that turns into 2 r squared minus x squared, right? Because we get, well, actually, let me go ahead and write that. So this is 2 r squared minus x squared equals 2x squared. So distribute this stuff on the left, And what we wind up with from here, by taking this and moving it over, is 2r squared equals 4x squared, or x squared equals r squared over 2. So since x is positive here, we're looking at r over root 2. All right. Okay, so we've went through a lot here so far. Now we want to do our critical number test here. So we put in our endpoints and our critical number. Let's see, and we're going to plug these into the area. So if we look at the area function, if we plug in 0 to this area function, we know we're going to get 0. Right? Maybe let me write that here. 2x squared minus x squared. It's going to be gigantic, but it's fine. Right? So if we plug in x equals 0, we get 0 here. If we plug in x equals r, the stuff under the square root is 0. So this is again 0. Right? If we plug in r over square root 2 here, we're going to get 2r over square root 2 times square root of r squared minus r squared over 2. So this is 2r over root 2 times r over root 2, which interestingly enough is just r squared. Right? Because root 2 times root 2 is 2, and then we have that 2 up top that cancels it, and there we go. So this is the max here, because the other ones are 0. So the question actually is asking, what is that largest possible area? And that largest possible area is this r squared. The largest area is r squared. Right? And that's it's a little bit interesting, at least to me here. The area of this thing is pi over 2r squared, because it's half a circle. And the largest rectangle we can fit in is basically just remove the constant that has to do with the circular nature of it. I just think it's kind of neat how that works out. Yeah, hopefully this gives you, a little bit of an idea of how we can sort of use this optimization process to, again, like get some interesting answers to problems and sort of see, like, maybe this particular problem isn't the most useful or the most interesting, but sort of the problem-solving nature of it, I think, is. Like, how do I set up my optimization problem? And, if you ever have to do anything, if you ever have to use this kind of stuff in a more practical way, that's always the challenge is, what do I set my objective function to be? That one's usually the more obvious one. But the real challenge is sort of like, what constraints can I use? How do I set a feasible domain? So hopefully this gives a little bit of insight into that. But so I'll just ask here, are there any questions about any of the 4 problems we did here before headed out for the day? All right, cool. So I plan to post these notes shortly after ending here. So these will be available on Notebowl, the notes that I just wrote up here today. And And this video will be on YouTube for you to watch at any time. Hopefully you don't have any issues with that, or any issues like getting on YouTube or anything like that to watch. I know it's part of Google, so hopefully that is a usable thing for some of you. Otherwise, yeah, any questions, feel free to send emails at any time. And take care. Have a good rest of your day. And I'll see you tomorrow.